for us. Okay, great. Got it. Okay, as I was saying, Professor Huang will have for us a very interesting talk on OCT, so optical coherence tomography. So please, Professor Huang.
Okay, thank you, Valentina. Good morning, Professor Donati and ladies and gentlemen. Yeah, thank you for joining this ieee activity. And I think I should also thank the ieee student branch at the Pavia University. Thank you, Valentina and Martina, for putting this program together. Yeah, and also of course, I should thank. You can hear? Okay, yeah. Yeah, and I think I should also thank the sponsorship of the ieee Photonic Society Distinguished Lecture Program. Yeah, I think this is my fifth visit to Italy, but the fifth visit in Italy, but my first visit in Pavia. But I have known Professor Donati for more than almost 20 years. But it's very happy. Finally, I have a chance to visit Pavia. Yeah. So for this talk, actually is about OCT, and this technology actually has been there for almost 30 years. Right now, it's widely deployed in many clinical settings. So I hope that this talk can give the audience a glimpse about the present status of OCT and the future trend. Yeah. And for those of you who are not quite familiar with Taiwan, but I think these days many people heard about Taiwan. Yeah. But I think for most of you not quite know about Taiwan, so I will give a very brief introduction about Taiwan. Taiwan is a very small island, as you can see here. So Italy is about, the area of Italy is about a factor of 9, larger than Taiwan. So this is a small island, but even though it's a small island, but in Taiwan, we have more than 160 universities in Taiwan. And among these 160 universities, about 35 of them, they have either the photonics college or department or graduate institute. Yeah, so photonics is something quite big in Taiwan. So according to the Optical Society of American, the market share of optics and photonics production, Taiwan covers, as you can see here, about 11%. For the mainland China, it's 22%. So even we are a very small island, but our photonics production is covered about half of from China. Yeah. Let me see the next one. Okay, so actually right now in Taiwan for the optics and photonics, the industry is mainly about ICT, the so-called information and communication technology. But these days, many of these companies, they have shifted their focus toward something biomedicine, especially in the so-called precision health. So in Taiwan, you can see here, we have the stuff from the foundry service, the TSMC. You may hear about MediaTek, which is MediaTek. That's for circuit design. We have Wistron, we have ASUS, Acer, for making the notebook, and also for some prototyping for small companies. So I think all of you here, they are welcome. In the future, you can collaborate with Taiwan. The infrastructure on photonics, electronics is quite complete in Taiwan. Then a little bit about my university, which is NTU. Professor Donati visited there many times. The NTU was established in 1945. In Taiwan, it's pretty old, but compared to Pavia University, we are pretty young. we are only 80 years old. I think for Pavia, it's more than 800 years. Is that right? 600. Okay, sorry. So we are pretty young. But in NTU, we have 11 colleges. And for the student population, we have, I think this data is old. These days, I believe we have 36,000 students. Yeah, the number of population a little bit larger than Pavia. And we have 16 campuses throughout the Taiwan island. Yeah, so you can see here the main campus of NTU, this one, is in Taipei. That's the capital of Taiwan. And then we have several other branch campus scattered in Taiwan. And we have the large one that's in the center of Taiwan. In Taiwan, we have, even though it's a small island, but the highest mountain in Taiwan is pretty high. It's almost 4,000 meters high. The summit of the mountain belongs to NTU. Yeah. So Silvano, you know that the main campus in Taipei is not small, right? But you only cover 1% of the total NTU space. And the total NTU space covers 1% of the total island. So we are probably very close to the largest in terms of area in the world for the size of the campus. Yeah. So this is about NTU. Okay, now let me start for the talk today. So for those of you who are not quite familiar with OCT, I will give you a very brief introduction about OCT. Then I will show you our recent work on cellular resolution OCT. Then I will say a few words about my personal perspective about the trends and the challenges of OCT in the future. Okay, so because for OCT is optical coherence tomography, so apparently coherent is something very important for OCT, right? So from your college basic physics, you know that in case you have two coherent light, they combine together, you will see depends on the relative displacements between the two coherent light, you will see constructive and destructive interference pattern. So you will see this kind of constructive and the destructive pattern. But in case these two beings, they are from an incoherent light source, then depends on the displacement. Only when the two waves have go through the exactly the same amount of displacements, then you will see a so-called coherent spike. So this is the envelope of this coherent spike. Actually, that's the OCT signal. So the basic principle actually is quite simple for OCT. Then how people use this kind of coherent interference to get imaging. Starting from, for example, as you can see here on the upper left-hand side, this is a kind of a device on the test. In this case, this is the skin. So you shine an instant light and you try to detect the backscatter light. Then because the backscatter light usually is pretty weak, so you try to use interferometer to detect, okay? So you have starting from the instant light, you have beam splitter, so you have a reference beam. This is another device on the test. For example, this is your eyeball. So this is a detection arm. Okay, so the configuration actually is quite simple, just like a Michelson interferometer, except that usually for Michelson interferometer, your light source is kind of a laser, it's a narrowband device. But for OCT, you prefer an incoherent light. Actually, the broader the light source bandwidth, the shorter the coherent spike I just mentioned, which means that you can have better imaging sectioning capability when you try to form an imaging. So using this kind of Michelson interferometer, you can have one-dimensional data. Okay, so whenever you see an interference difference between two arms, you will see a coherent spike. So in this case, you see many spikes. That means there's a index discontinuity. Then in case for your sample, you have a one-dimensional shift, then you can acquire a two-dimensional imaging. In this case, apparently this is a human cornea. Okay, so in case your device you have a two-dimensional imaging sensor, or you scan the device on the test, so you can acquire a 3D tomogram. Okay, so this is actually a video, but I don't know how I can play. Can you show how to play this?
You have to exit one for a while.
Okay.
And then
Yeah. Okay. So later,
so you have
I have many videos.
Okay, so you have to exit from the laser pointer mode.
Okay, got it. Thank you. Yeah. So you see the video. So the different two-dimensional imaging actually is different depths within the sample. The nice thing for OCT is that you can have very high imaging rate, okay, and it can have a high resolution. When I say high resolution, means that you can have 1 micron level or even some micron level resolution. For the high speed, I mean that you can get this kind of 2D imaging kind of in real time. So it's very fast, high speed, and high resolution. Okay, and as I just mentioned, for OCT, actually, the optical sectioning capability depends on the light source. So you can see here, the broader the light source, then you can have the higher the actual resolution you can have. Okay, so this is the basic operation principle of OCT. And for this technology, actually, it has been invented for about 30 years. So you can imagine these days people use OCT for a number of different applications. But among them, the most popular one is for one example is for ophthalmology. Okay, so people try to see using the OCT to examine the retina or the anterior segment. So on the lower left-hand corner, you can see this is a typical OCT imaging on retina. Okay, so within the human retina, actually there are roughly about 10 different layers. But these days, because of OCT, actual resolution become higher and higher, so people can see all the different 10 layers within the retina. Okay, and another big application is in cardiology. Okay, so people use the OCT, this kind of intravascular imaging. So you have a probe and into the vessel, especially the coronary vessel. So you can have this kind of 3D imaging. So people use this OCT to examine whether the stent, well, when your vessel is start to clog, so you got to examine whether you need to add in a stent, yeah, to check whether it's properly installed. Okay, and also within the coronary vessel, sometimes you have some plaque within the vessel. So you can use OCT to check whether that plaque is kind of vulnerable. Yeah, so number of possibility for using OCT for intravascular application. Okay, so because OCT has been there for 30 years, okay, imagine there are a number of different schemes or configurations that people use OCT. So as I just mentioned, OCT basically is an interferometer. So these days you probably hear about the time domain OCT, the spectral domain OCT, the spatial domain OCT, the full field OCT, or the swab source OCT. The basic principle are all the same. Okay, just depends on how you use the light source, how your reference arm, whether it's a fixed reference arm or it's a moving reference arm, and also depends on in the sample arm, which is this is the sample arm, this is the detection arm. So it depends on how, in the sample arm how you scan your device on the test. In the detection arm, whether you are using a point detector or you are using a detector array. Okay. So if you want to acquire a 3D tomography, okay, so there are a number of different possibilities. So different groups in the world, they use different schemes. But among them, these days, the most popular one is the swab source OCT. The other one is the full view, because for these two schemes, the imaging speed is very fast. Okay, the line scan rate can be a million 8 scans per second. So it's a very fast imaging technology. Okay, then a little bit about the literature survey. As I mentioned, OCT was invented in 30 years ago in 1991 by Professor Fujimoto at MIT. Then I think in Professor Fujimoto's work start from the ophthalmology for the inspection of retina. And later on, people use OCT for cardiovascular. So you see that in terms of the vertical axis of this table is the number of publication. Yeah. In case you have more publication, then you can imagine you are going to have more market size in the future, right? So starting from the growth of ophthalmology, cardiology, neurology, and these days also the dermatology is picking up, and also for the GI, the so-called GI tract, okay, also growing. Yeah. And in the early days, from I think before year 2000, at that time, most of the OCT development, people care about how fast you can imaging, because for OCT is kind of in vivo instrument. So because the human body, your breath, you have blood flow, so you got to be very fast, else your image will blur. So after year 2000, people care about not just only the imaging speed, people care about the higher resolution, because once you have a higher resolution, you can see the cell, because many diseases depends on the cell, how the shape of your nuclei, how many the nuclear density and the boundary of nuclei, whether it's a smooth or it's a rough boundary. Yeah. So up to this year, I think people care both the imaging speed and the imaging resolution. Yeah. So this is about the paper. So in case you have more and more papers, so you can imagine that the market of OCT also kind of picking up. So the largest one, apparently, even these days, in ophthalmology, right now worldwide, there are more than 100 OCT companies. Among them, roughly about 80% of the company working on in the ophthalmology. Okay, there are roughly about 5 to 10% on cardiology. Okay, and these days you see the dermatology, this light pink one is also getting this part, yeah, also getting bigger. So you can see that the average growth rate is pretty high, more than 15% per year. This is in terms of the application. And because OCT is kind of a system, right? So within this system, I think for the market, mainly I think it's about the OCT system, but for the OCT light source and some modules also have some relative reasonable amount of percentage for the market size. Okay, and because for OCT, this is a kind of imaging modality, so you can imagine, and I mentioned that it's a high speed, high resolution. So you can imagine the amount of data is huge, okay? So there's a lot of possibility using the so-called artificial intelligence on OCT, so you can get more information out of this huge amount of data. So for artificial intelligence, actually, this is not a new term, right? Starting from year 1950, okay? People talk about AI, then starting from 1980, people talk about machine learning. And in recent years, actually, after 2010, people talk about deep learning. I think deep learning is something quite match OCT. Why? Because as you can see, the figure on the upper right-hand side. So when you have the horizontal axis is the amount of data. So in case you use the conventional machine learning algorithm, then the performance of the machine learning actually is kind of saturated when the data become large. But for deep learning, okay, the larger the data set you have, the better the performance. Okay, so deep learning actually is kind of very best matched with the OCT. Okay, because we have the very large amount of data. So you can see that over the years, people use the AI on medical imaging, not just the OCT. Okay, the AI is very important for all kinds of imaging modalities. So it's growing very fast in the past few years. This is one good example. This is the company, DeepMind it was a company in United Kingdom, but later on it was acquired by Google. And so they use AI to analyze the OCT imaging in the retina. Okay, so they can segment the layers, they can do some disease early detection. Okay, yeah, so I think in the coming few years, you can imagine that there should have more and more companies that evolve to try to fully utilize the deep learning on all kinds of imaging modalities. Okay, so this is the last page for my introduction about OCT, because the OCT technology is something very important. As you can see here on the upper left-hand corner, the severity of a disease, usually people can feel that whether there is some disease, but this kind of functional perception will change it kind of binary. The structure of your physical structure actually change linearly. Okay, so many times in the early stage of a disease, you cannot feel there's something wrong. But for OCT, because it's detecting the structure, Okay, so you can even see something, detect something before you observe, you're aware something wrong. For example, for your eyesight, right? So in the early stage, if you have something wrong, you don't have any feeling, OCT can check that. Okay, and these days, OCT or from now or in the future, in the one hand, you can have very high spatial resolution to see the structural change. Also, with a cellular resolution or high resolution, you can see the cells, either whether it's a necrosis cell or apoptosis cell or the cellular interaction. Okay, this kind of structural information. Then because OCT, the imaging speed is very fast. So out of this data, actually, you can also try to extract some dynamic or spectroscopic information. Okay, so from this information, you can analyze using the deep learning to find the activation pathway or even system coordination related to disease. Okay, so if you combine the structural information and those dynamic or spectroscopic information in the future, we hope that using OCT you can have early disease diagnosis. Okay, so that's about a very brief introduction about OCT. Now let me show you some of my work for using cellular resolution OCT. Okay, so for cellular resolution, this will give you an idea what do I mean cellular resolution OCT. So the end-phase view here, you can see that's the for the skin imaging at different depths. So this is a video. And on the upper right-hand side is the cross-section, means it's perpendicular to the light instance. And because it's very fast, so you can see a movie here, you can see the red blood cell. Okay, so this is a very high resolution, high speed. And another good thing for OCT is that you don't need a very high power to probe your the patient. So the power level on the tissue actually is only about less than 3 milliwatt. You know that for the typical red pointer, the power is more than 5 milliwatt. So for OCT, even lower than the red pointer. So it's a very safe, very high resolution, very high speed technology. Okay, so this is another example on this is a rapid model. Okay, so from the cornea, you can see the cornea structure at different depths. Okay, so for human cornea, you have a cellular structure. Also, there's some nerve. Okay, in the bottom layer of the cornea. So as you can see here, this is the Bowman layer of cornea, and you see some fibrous structure. That's the so-called subbasal nerve. Okay, actually the subbasal nerve, there are many information there. For example, the density of those fiber, the length of the fiber, and also the kurtosis of the fiber. It's all related to many diseases, not just for the eye, even some mental or dementia diseases also related to the structure of these cornea nerves. Okay. Okay, this is another example. This is the endothelial cells. You know, endothelial cell apparently is the deepest tissue within the cornea. So the number of endothelial cell just decreased after we get birth. So this is a good indicator whether your eyeballs healthy or not. Okay, and from this endothelial cell, you can see also as I mentioned, the subbasal nerves. Okay, the nerve fibers. There are many informations there. Okay, then when I first talked to many physicians about the cellular resolution OCT, many physicians they just don't quite, because for OCT imaging, it's a kind of black and white imaging. On the right-hand side, you see two OCT imaging. It's black and white. So this kind of imaging actually is not quite familiar for those typical physicians, because for the physicians or clinicians, when they are a medical school student, they learn about anything about the hematoxylin and the eosin stain imaging. So for all the physicians, they are very familiar with the image on the left-hand side, but they have no idea about the black and white imaging. So we collaborate with many physicians. So we got to show that we really see the cells, see the nuclei. So we have some one-to-one comparison. So as you can see here, the hair follicle on the left-hand side and on the right-hand side, the fat cells. Okay, so even for a very small dimension or for large dimension, there's kind of a one-to-one comparison. But still, these days, it's still very difficult for the physicians to read those black and white imagings. So this is something really the artificial intelligence could help, okay, to try to color this black and white. So for the physicians, it's easier for them to read something out of the black and white imaging. Okay, so this is but for this kind of optical technology, as I mentioned, the resolution is high, the image speed is high. The major problem for optical technology usually is about the penetration depth, how deep you can penetrate into the tissue. So that depends on a number of things. For example, in this slide, you can see on the upper left-hand side, we use a visible light. When you use a visible light, the total penetration depth from here to here roughly is about 100 to 150 micrometer. But on the right-hand side, we use a near-infrared light source. Then the penetration depth becomes deeper. So in this case, from the top layer here to the bottom here, totally is about 350 to 400 micron. But even though 400 micron, you may think, wow, it's really too shallow. But usually for most of the skin diseases, it's originated from the so-called thermal epidermal junction. Okay, so in this slide, as you can see here, from here, I'm just trying to outline the thermal epidermal junction. So most of the skin-related diseases is originated from there. So typically, the thickness of the thermal epidermal junction only about 100 to 200 micron. Okay, so that's good enough for OCT to come through. Yeah. So the penetration depth depends on the wavelength. Using the near infrared is deeper. Apparently, the penetration depth also depends on your skin, right? So in my laboratory, I have an Indian student with a dark skin, Taiwanese, and Spanish light skin. So you can see, apparently, for people with light skin, the penetration depth is deeper, right? Yeah. Okay. Okay, so once you have this kind of 3D tomogram, apparently you can do something to help to facilitate physicians to read the imaging. So a few years ago, we used the machine learning, try to segment the nuclei. Okay, so for the physician, it's easier for them to read. But because this is the machine learning, so it took more than 5 hours to do this computer job. Recently, we tried to use the deep learning, so hopefully you can do real time to do this kind of nuclei segmentation. Okay, now so this is about cellular resolution OCT. And using this very high resolution OCT, we have to do some starting from some in vivo and the in vitro study. And very recently, we start to have some in vivo clinical trial in hospitals. Okay, so this is a mouse squamous cell carcinoma model. That's one of my collaboration with our university hospital. This morning I heard that in University of Pavia, you also have a kind of university hospital. Yeah, so that's very important to collaborate with the physicians. They know what they need, right, what they want, right? Yeah. So for this model, it's actually very simple. We just try to introduce some chemical. So here is a DMBA-TPA, just a chemical toxic chemical. So you apply on the skin. So starting from a healthy mouse skin, after 1 or 2 weeks, the skin become into the dysplasia, kind of abnormal status. And after maybe 1 month, you start to see the tumor. That's the squamous cell carcinoma. Okay. So for this animal model, so for each of the mouse, we do have the hemataxilin and the using stem cell. That's kind of the ground truth. And we have our OCT imaging. So we'll try to see whether using the deep learning, whether from this OCT imaging, you really can classify your imaging into tell whether it's a normal skin or it's a dysplasia skin or it's a squamous cell skin. Actually, the accuracy is pretty high. As you can see here, usually the classification accuracy can go to 95%. And we try to, some people ask one question, well, using this OCT, you really can precisely classify the imaging to know its status, but whether this accuracy related to its high resolution. Okay, so we try to kind of use a numerical technique, the so-called downsampling. So we try to blur the imaging. Okay, so the 2 means that we reduce the resolution by a factor of 2, and gradually you can see that once the imaging becomes blurred, so the actual the accuracy start to decrease. So this means that high resolution is very important to give you a very high accuracy. Okay, this seems to me this is a common sense, but many physicians ask the question whether high resolution is needed. Yeah, so you got to show them that, well, it's really needed. Yeah, and also some people criticize about the deep learning is that, well, in many cases from the newspaper literature, people say that, well, deep learning something work very nice, but the problem for deep learning is that it's kind of a black box. It gives you a good result, but you cannot tell why the deep learning do something right. Okay, so people care about whether you can, how do you know, even though the deep learning gives you the correct result, what's the key feature that make the deep learning help make the correct judgment? Okay, so we use the so-called GradCam technology. So you can see, remember we have 3 different OCT imaging. One is the normal, one is the dysplasia, one is the cancer. Okay, so using the so-called heat map. The heat map means that those colorful location means that those locations are important for deep learning to make the decision. Okay, so from the HM1, this is the HARMAP 1, HARMAP 2, HARMAP 3. The different HARMAP means that whether the deep learning is looking at a very small area, or the deep learning is looking at some large area. So HM1 is looking at the very tiny features. HM4 is on larger features. So as you can see here, the bright spot or the colorful spot are all the nuclear sites. Okay, so which means that the deep learning algorithm, they are really looking for the important features, because the nuclei is something very important for physicians to make a judgment whether this is a normal cell, or this is a cancer cell, or this is a abnormal cell. So the deep learning also looking at those nuclei. Okay, so then that's for animal model. And very recently, we are collaborating with MS Memorial Sloan Kettering Cancer Center. It's located in New York. So there are 2 physicians, Drs. Manuel Jian and Dr. Jason Chen. So they are dermatologists. Okay, so they, because in the United States, or even in New York, in Europe or in Australia, there are a number of people have the skin cancer, right? Okay, just in the, for example, in United States, each year the new instance is more than 3 million. Okay, 3.5 million new instance for skin cancer. Okay, so they have a lot of patients. Okay, so we have a kind of clinical study in New York, but this is a ex vivo case. So on the upper left-hand side, you see this is the black and white OCT, and they always try to have excision with this kind of stain imaging to give you the ground truth. Okay, so for the physicians, from based on this, this is the image size here is a few centimeters, so it's very large. So you can enlarge here to see more detailed features. Okay, so usually for the pathologists, they need to see the details. So the arrows means the physician, they look at the imaging, they can detect something wrong from the imaging. Okay, so the physicians at the MSKCC, they try to annotate both the stain imaging and our OCT imaging. Okay, so this is serves as the ground truth for the machine, for the deep learning. Okay, so right now they have about 180 kind of patients. So we have many these kind of pairs. Okay, so using the deep learning, so we try to see whether when you input these black and white imagings, whether you can detect where is the tumor boundary. So this is the second column is the annotation by the pathologist, and the third column is using the convolutional neural network. Okay, so this is kind of a qualitative comparison. You can see the the yellow line here, this is a true positive. And so it's matched pretty well, but we do have many, this pink is a false positive. Okay, so qualitatively, you can see that it's not bad, okay? So we also have some more quantitative assessment. As you can see here for the, this is a nodular basal cell carcinoma. The detection accuracy can go to almost this 87%, okay? For this SOVO is almost 90%. Yeah, so basically for the detection of the skin cancer, the accuracy is reasonably high. I think in the future, in case we have more patients, okay, I think the accuracy can keep on increasing. And another possible application for this kind of cellular resolution OCT is for in vitro application, because for many new drug development, the experiment is done in vitro. As you can see here, this is a melanocyte, this is a melanoma. So apparently this is a malignant cell. So you can see that a normal melanocyte and the malignant melanoma, the image structure is quite different, right? For the melanoma, you see many different kind of microvilli grow out of the cell. So using this kind of imaging, you can serve as a kind of image biomarker. So on the right-hand side, you see that many of the features are very can be used to discriminate whether the imaging is from a normal melanocyte or a malignant melanoma. Most of them are the p-value is less than 0.001. Yeah. So this is for in vitro applications. And another way, another important possibility is for these days for cell culture. You start to have a more complex culture, not just cells. Sometimes you can have organoid. Okay, it's a mere organ, right? But just not that fully grown organ. It's a organelle, so-called. So using OCT, you can see the cellular structure at different depths. Okay, and this is one of our collaboration with NTU hospital. Yeah. So I have the list of our publication there. So in case you are interested in this technology, you can check our paper to see more details. Yeah. So this is for in vitro application. So once we have the ex vivo, in vitro, and on the human, so I think started from 2 years ago, we start to have some in vivo application, because in vivo is something very close to patient. It's something really can generate the impact of OCT, because as I mentioned, OCT, the light source is very safe. So it's very good for in vivo in clinics applications. So I have, just like Professor Donati, I have established a company called Apollo Medical Optics. So they have a prototype, is FDA approved. So using this machine, right now we have a collaboration with the hospitals in Taiwan, which is the Mackay Hospital. We have a collaboration with the MSKCC that's in New York. We have a collaboration with the hospital in Berlin. Okay, yeah. So using this kind of in vivo system, because for this in vivo imaging, as you can see here from this black and white imaging, you can find out the thermal epidermal junction. That's something very important. You can find out within the epidermis, there are many different layers. For example, the stratum corneum, the stratum granulosum, and the stratum spinosum. Okay, and in the dermis, you have the microcapillary, you have a small vessel, you have sweat duct. Okay, you have even the melanin. Okay, but for most of you, when you look at this black and white, maybe you cannot read out these features. But for the physicians, when they see this kind of imaging daily, they start to catch up to understand how to read this in vivo imagings. Because for this 2D imaging, the time is when I prepared this slide, it's 2 seconds. Now it's less than 1 second, which means it's very fast, almost immediately. Okay, so this is one of my clinical trial in Mackay Hospital in Taiwan. Okay, so you can see that for the basal cell carcinoma, this is using the conventional after biopsy. You try to stain. You have the stain imaging. On the lower left-hand side, this is the OCT imagings. Okay, so the physician try to mark what the important features. On the right-hand side is a EMPD. It's also kind of malignant disease. Okay, so we have the HE stain and the OCT, and this is a melasma. Okay, in case on your skin you see some kind of a navy. Okay, nevus. Okay, whether it's something just a normal or it's a malignant. Usually by just using the conventional tool people call the thermoscope, it's very difficult to judge whether it's a melasma or it's just a nevus. But using OCT, there are many features you can find. Okay, and this is for another application for many these days for cosmetic dermatology, or people call aesthetic medicine. So people use the laser to treat your skin. For example, you have a nevus, you want to use a laser to remove those nevus. Okay, so you can use a laser to drill a hole in your skin. Okay, this is so-called laser-induced optical breakdown. Okay, so this laser can just disperse the melanin. So then the skin color will restore to its normal color. So without OCT, you really can see, for example, what is the size of the laser-induced optical breakdown, what's the depth. Okay, so with the OCT, you really can have a precise determination of the treatment, the efficacy of the laser treatment. Okay. Then because this kind of OCT, as I mentioned, because it's black and white, so it's very difficult for physicians to read. So recently I collaborate with the Marquette Hospital. They try to prepare a kind of a guideline for many different kinds of skin diseases. We have the OCT imagings, we have the stain imaging. For in the future, for physicians that are not familiar with this kind of OCT, they just look at the guideline, they can try to read out this kind of cellular resolution OCT imagings. Okay, so this is pretty much about the second part of my talk. Then in the future, apparently you can OCT here, starting from the invention of OCT 30 years ago, you can imagine, because if you remember the publication, right now it's still growing, so you can imagine in the future, there are many possible new applications that could be developed using OCT. So as I mentioned, I just list some of my personal perspective. What's the future trend? One is about the functional OCT, because originally OCT just gives you the kind of structural information. Okay, there's no functional information. So how can you try to obtain functional information? As I mentioned, OCT was invented by Professor Fujimoto in MIT, but actually at the time, one of his co-authors is Dr. Eric Swanson. He has he built a web called OCT News. Actually, they update all the new information about OCT bi-weekly. Yeah, so if you look at this web, you will see what's the new light source, what's the new application, okay, what's the new clinical trial of the information. So from this OCT News web, I try to summarize what's the possible application in the future. So one important application is the surgical guiding, right? Especially during, you can imagine during the skin cancer, in case you want to remove the tumor, okay? So you can see that there's a dilemma. In case you have a malignant tumor, in the one hand, you want to remove the tumor. If you cut if you have a larger biopsy, you can remove the tumor clearly. But in case with a larger removal, then you hurt your skin, right? So so it's better that you can precisely determine where is the boundary of the tumor, so you can precisely remove the tumor. Okay. So during the surgical, in the past, the physician got to have a biopsy, then send to the lab to have the stain. And once upon the stain, they know where's the margin and go back to the operation room. But for the biopsy, typically even for frozen biopsy, it took hours to do that. Okay, so the patient suffers. But using OCT, you can, as I mentioned, the imaging speed is very fast. Just within seconds, you know whether there's where's the boundary. And for the functional imaging, what I mean is that, for example, within our human body, there are many dynamic information. For example, you have blood flow. So what is the flow rate of your blood cells? Okay, what is the flow density of the blood cells? So those are related to the diseases. Okay, so that's what I mean, functional imaging. Okay, and optical biopsy is also something quite important because usually, especially for cancer diagnosis, right now the gold standard is using the so-called HE staining. That's the gold standard. Okay, so most of the physicians, they know how to use the HE stain to make a diagnosis. But there are some statistics that worldwide for the biopsy, only about 10% of the biopsy shows that, well, this is really a malignant tissue. It's not a benign tissue. Okay, so many of people, they have one cut, but actually found that, well, this is actually benign. Okay, but using the optical technology, it's kind of virtual, right? We just take imaging. There's no physical biopsy. So in case from there, you can have better accuracy. And many people don't need to have this real biopsy. Yeah. And also another important possible feature is that because for the pathology or histopathology, people use the biopsy. Even for the biopsy, for example, the HE staining, the resolution is very high, but the resolution is high only on in the lateral plane. But actually, for each of the slide, there's a thickness. The thickness is about 10 micron. But in the lateral direction, the resolution is about 1 micron, which means a cellular resolution. But in the depth, actually, is pretty thick. But using OCT, actually, it's kind of isotropic resolution, which means that in the lateral direction or in the vertical direction, it's all micron or submicron. Okay, so actually, from the OCT, in the one hand, it's a black and white. It's not something good. But on the other hand, it's a high resolution in all the directions. So actually, in case when the physicians start to really learn something, know how to read the OCT imaging, they could have new scientific finding about the human structure. Okay, so there's a biomedical magazine. It's called Biophotonics. Okay, they try to, because for finding the tumor margin during the operation is something very important. So worldwide, there are many different imaging modalities. People try to find out where is the tumor margins. So this graph here is very interesting. You see many different rings, okay? And there are many different technologies. So for the outer rings, that means the technology is basically in the laboratory, okay? So near the center, that means this technology is closer to daily use, okay? And you see different quadrants, okay? So for this quadrant, that means the imaging modality is label-free, okay? So you don't need any biopsy, you don't need any putting some fluorescent dye, okay? And on the right-hand side, this is with a label. And on this corner, this is a multi-modality. So among this technology, you can see that using OCT on skin cancer is very close to clinical use in hospital. Then for OCT, because as I mentioned, for OCT, we are detecting interference by two incoherent light. Okay, so we see the coherent spike. But usually for image formation, we only use the envelope of the coherent spike. But beneath the envelope, actually you have a very broken light sources. That's the information. Okay, so using this information, you can try to find out any dynamic property or spectroscopic property. Okay, so because for OCT, usually for imaging analysis, people usually call the Hilbert transform. But we can prove that the Hilbert transform is actually identical to finding the standard deviation when the reference arm is not moving. Okay, so using this information, you can get some dynamic information or functional information. This is one example. We're trying to find out whether there's as you can see from the left-hand side, this is the absorption curve for hemoglobin, or whether the hemoglobin is attached to oxygen ion or whether it's attached to carbon dioxide. So you can see here with different kind of hemoglobin, the absorption is quite different. Okay, so for example, you can see here, in case the hemoglobin is attached to carbon dioxide, the absorption is very low. But in case the hemoglobin is attached to oxygen, then the absorption is high. Okay, so using the OCT from different, the different color means that the different optical strength, the intensity. So you can find out what's the relative ratio for the blood cell, whether more percentage is attached to carbon dioxide or more is attached to oxygen. And also, because for OCT, you use a probing light source, as I just mentioned, if you fully utilize the spectroscopy information, you can find out the depth-dependent spectrum. So this is an in vivo case using my student as the subject. So on the left-hand side, you see different depths, you have a different structure, and so it's a relative backscatter spectrum you can see here. Okay, so we try to collect more data. So in the future, you are not just look at the structural information. You can also look at what's the change of the spectrum related to different depths. You can find out more functional information. This is another example for the so-called dynamic OCT, because the image spins very fast. You can find out what is the on the right-hand side. You see the average velocity mapping. Okay. And you can also try to segment out what's the vasculature of your blood vessels. Okay, yeah, using different kind of algorithms. So that's so one trend is using the OCT to get the functional information. Another important trend is about the so-called sweat source OCT. Okay, using the sweat laser source. And I copied this slide from Professor Fujimoto. Remember, he's the inventor of the OCT. So he tried to summarize why people in the future want to use a sweat source as the OCT light source. So because sweat source OCT is faster than the so-called spectral domain OCT, and you can use because for the spectral domain OCT, people use the CMOS sensor grating and the sensor. So the wavelength is kind of shorter, but using sweat source, you could use a longer wavelength. Okay, with a longer wavelength, you have deeper penetration, okay? So you can see more features. Okay, and the sweat source is also very fast. Okay, so a number of good property of sweat source. So in my laboratory, we also try to, but these days for the sweat source OCT, people can have very deep penetration. People can have very fast imaging speed. But the problem is that right now there's no cellular resolution sweat source. So in my laboratory, So this is one example. People try to show that why you need a cellular resolution sweat source. This is a paper published by Harvard University. Because right now, when OCT is used in cardiology, these days in many hospitals, they do have this kind of intravascular OCT, but their resolution typically is about 10 micron to 50 micron, which means that it's not cellular resolution. So from this paper, it showed that, okay, for some of the very important information, for example, within the coronary vessel, you could have some plaque. So whether the plaque is a normal plaque or is a vulnerable plaque, right now in the hospital, the typical gold standard is that because for the plaque, is a thin cap, depending on the thickness of the thin cap. So in case the cap is less than 65 micron, that means, well, this plaque is kind of safe. You don't need to worry about the rupture, okay? But many clinical evidence show that this is really not a good kind of clinical standard. So in the future, people do need a higher resolution to have better clinical assessment criteria. And for the stent, usually after for the patient, you install the stent in your coronary vessel. You need to go back to check again whether the stent is well positioned. Okay, in that case, people also need a very high resolution to see that whether you have a single epithelial layer, then that which means that your stent is properly installed. So all these two application, you need a cellular resolution OCT. Okay, so in my laboratory, I also try to develop a swab laser. In the one hand, the sweeping rate is very fast. On the other hand, also it's a sweeping wavelength range is very broad, so that you can have high speed and high resolution. Okay, as you can see here, right now the sweeping bandwidth actually is pretty wide. It's more than 200 nanometer, which means that this light source can be used for cellular resolutions, light source OCT. And right now the speed is not very fast. It's only up to about 1.2 kilohertz. Okay, so in the future, we are developing a faster sweeping rate. So this kind of laser can serve as intravascular cellular resolution OCT. Another, I think, important trend in the future is that because these days for the silicon technology, we know that for the foundry service, Intel, Samsung, or TSMC in Taiwan, they are very mature and very low cost semiconductor chips using the CMOS technology. So for the silicon photonics, actually in the future, there are a number of roles that can be applied to integrate with OCT. So you can make the system be portable, be more economic. Okay, so using the silicon photonics modules, for example, the 2D CMOS sensor, something very important. You want to have a very small pixel, so you have a higher resolution. You want to have a higher imaging rate, right? So that's something also very important. Also, for the silicon photonics, you have many different waveguide components. Either is a coupler or photo detector or mass scanner. So a number of, I think, silicon photonic technology using the so-called foundry service that can really help the OCT technology to miniaturize and to cost down the system cost. So actually, there's already, I think this paper was published by the group in Belgium. So they do have a kind of silicon photonics based OCT system. Even though right now the performance is not quite significant, but when people start to improve the device performance, and I think in the future it's quite promising to have a very economic silicon photonics based OCT. Yeah. Okay. Finally, some very important feature I want to. Do I control my time? Okay. So it's past 12, so I better speed up on the last part, because this is also quite important, because using OCT right now we have a very high resolution, but because it's black and white, so it's not easy for the physicians to read. So recently, especially for cancer diagnosis, people need a very high resolution. For the OCT, with a broken light source, you can have a micron level resolution, but actually the resolution is based on the so-called radial criterion. But actually from the backscatter pattern, actually we have shown that even from the scattering feature, you can see even up to 50 nanometer of particle information can be acquired from the backscatter light. Okay. So this is an example that we're trying to achieve. On the left-hand side, you can see that this is HE stain imaging. So it's colorful. And for most of the physicians, they can read where is the tumor, okay, where's the anomaly. On the right-hand side, this is OCT, so it's black and white. So we try to see whether we can translate or convert the black and white imaging into this colorful imaging. Then it will be very easy for the physician to read. And these days in the so-called artificial intelligence field, it's very popular. People try to do the imaging translation. On the left-hand side, you see this is a style from a kind of both the picture to a kind of painting. You can translate the imaging, or from the winter, you can translate into a summer. But this kind of image translation, well, you can see that the effect is pretty good. But for biomedical application, this is something very serious, right? If, in case you translate the imaging, in case it's not accurate, well, then the physician may have a wrong diagnosis, right? So the only difference compared to the normal image translation for the OCT, you need to have a very highly precise image translation. Okay, so in my laboratory, actually, we try to have develop a new algorithm. Okay, we have two data sets. One data set is coming from the OCT, so we have thousands of OCT images. On the other hand, we have a lot of HE stain imaging. These two data sets all are big, but they are not one-to-one correspondence. Okay, so we try to train the artificial intelligence network. Okay, to see whether you can translate the OCT into the stain imaging. So this is the result. So on the left-hand side, you can see you have 4 typical examples. Okay, that's the black and white input imaging. Then after the algorithm, you can transform into the pink, something like the HE stain. Okay, so I cannot say that this translation is very accurate, but at least some of the feature is accurate. For example, as I mentioned, the thermal epidermal junction is important. So you can see from the left-hand side, this green curve, and on the left-hand side and right-hand side, they are matched quite well. And also for on the left-hand side, you see the nuclei distribution. And on the right-hand side, they also match quite well. So at least for this translation, the thermal epidermal junction and the nuclei location, nuclear density are matched quite well. Okay, so we have some quantitative measure. As you can see, the right-hand side, at least a reference here. So in case you are interested, you can see more details. But the one problem for the previous slide is that the reason we can have an accurate translation because we need a physician's annotation. They try to annotate where is the thermal epidermal junction, where is the bottom of the straightened cornea. But usually you know that physicians usually are very busy. Okay, so they don't have much time to help you to label your imaging. So we also develop a unsupervised algorithm. So we don't need a physician's annotation. We just have a large data set. One is OCT, one is HE. So our preliminary results shows that quite promising. As you can see that from the OCT, you can convert into the HE stain. Look, not too bad, right? And on the right-hand side, it's from the HE stain back into the OCT. Then you may say, well, why we need to convert the HE stain? Why we need to convert this HE stain image into OCT? Because for OCT, the new technology, and right now we know that from the OCT, you can read the nuclei, you can read the thermal epidermal junction. But actually, within the image, there are many other different spatial cells. For example, the Merkel cells, ganglion cells. Those kind of information right now we cannot detect or we cannot read the black and white. But in case we have HE stain imaging, we do have those Merkel cell, ganglion cell. Then we get the idea. Okay, when you convert into the OCT, what they might look like. So in the future, maybe you can use OCT to detect more information. Yeah. So these are our preliminary results. Okay, so this is the summary of my talk. Yeah. So first of all, I think I can convince you that the cellular resolution OCT can review the nuclei morphology, and where we can validate that. And AI is something very helpful for OCT to extract more information. And I think in the future, this kind of OCT, you can link the OCT with other imaging modalities. You can get more information. Okay, so for this talk, I got to acknowledge many of my collaborators. So for the OCT light source, we have a collaboration with the ieee, which is the Industrial Technology Research Center. I have collaborated with Professor Donati for several years on the light source. And we have collaborated in Taiwan, starting from a few years ago. The government put in a lot of funding on artificial intelligence. So we have a large funding. So we have collaboration with our Professor Homer Chen. And I have established a new company called Apollo Medical Office to commercialize the system. And I also have many collaboration with hospitals worldwide. Okay, so yeah, I showed this already. And thank you for your listening. Yeah. Any questions? Welcome. Yes.
So did I understand correctly that for ophthalmology applications, a wide spectrum source is preferred, while in other medical applications, flat sources? Did you get it correctly or not?
What do you mean for flat source?
Yes.
Yeah. Well, for example, remember for this kind of OCT, we have a 3D homogram. To acquire 3D, we have two ways. One is you have lateral slides. You combine the lateral slides to form the 3D. You can also have a number of cross-sectional slides, so you can form the 3D. Okay. So using the flat source OCT, you can imaging from the cross-sectional to form the 3D. Because depending on the tissue, some of the tissue you prefer to see the end pass, the lateral image first. For some of the tissue, you prefer to see the cross-sectional first. So in case for example, for the vessel, we prefer to have those cross-sectional imaging. So it's better to use threshold for OCT. Yeah. So for the cornea, you want to see the endothelial cell. So you prefer to have the end-phase imaging. Yeah. Right. So it really depends on the application. But in terms of speed, right now using threshold OCT and using a full field OCT, the speed is comparable. Okay. The only difference is that whether you have the end-phase fast first or you have the cross-sectional image first.
When you say first, you mean the operator seeing that thing first on the screen without any post-processing, so real time. Yeah,
for example, for threshold, it's very fast to get this cross-sectional imaging, but it's slow to get end pass. Yeah.
Okay, thank you so much.
Congratulations for your superb talk. And I have a lot of questions, of course, but I will focus on just two hardware questions. One, your images are beautiful and don't show any speckle effect. But usually when you have coherent light, you should have speckle. Why don't you have speckle? This is first. Second is, how did you scan the laser, the sweep laser that we have shown the titanium sapphire? That is, which mechanism did you employ?
Scan laser. Yeah. Okay. Yeah. So the first question about the speckle noise. Yeah, this is something very important. For conventional OCT imaging, it's very easy. People can detect where is the speckle. Okay, so this is a conventional OCT imaging. On this imaging, people actually can very easily see that, well, it's kind of noisy. So people know what is the noise. But for cellular resolution OCT, actually it's more difficult to identify whether you see some tiny spot, whether the spot is a kind of speckle noise or it's a real. It could be real, yeah. Because both of them, the physical size is about micron level. Yeah. So if you read it from our okay, so from our imaging, if you really want to see, well, you see some tiny spot, whether that's real or it's a speckle noise, it's more difficult, first of all. But by definition, there's a way to distinguish whether you see a spot, whether it's a speckle or it's a true. Because for speckle, it's kind of a random process. Okay, so if you image the same location, in case there's it's a speckle, that means at different time, the result should be slightly different because the speckle is a random process. But in case it's a real backscattering of organelle, then the image should be the same, right? So they do have a way to distinguish. But just that for this kind of high resolution, it's more difficult to identify. But for conventional, actually, it's very easy. Because, for example, in case you have a resolution 10 micron, whenever you see a 1 micron spot, you know this is a speckle, right? Yeah. So this is a very good question to how to distinguish these two. Yeah. As to the second question is about for the thread laser, how we scan, right? So that really depends on what kind of application. Because in case it's for skin, then you can just use the either MEMS, okay, or mirror to scan to have a.
I mean a scanning welding. Make the sweep.
Yeah, make a sweep. Okay. Good question. For the sweeping, right now in the paper I just show you, we use the conventional sweep laser. We use a mechanical mirror. That's why our scanning speed is only 1.2 kilohertz. So that's a little bit too slow. So for the sweep laser, recently there's another technology called Fourier domain monarchy. Using the Fourier domain monarchy, not the conventional monarchy, the Fourier domain monarchy, then it's a sweeping speed can go to mega kind of megahertz kind of speed. And that's something right now in my laboratory, we are working on that. So in the future, I hope that Professor Donati can help. We can develop this kind of Fourier domain monarching using the very broadband gain median. Yeah, I think that will be something very important. So in case we can have a disulfide-based Fourier domain monarching, we can have a serial resolution with a megahertz scan rate. That's something perfect for many applications. Yeah.
Good. A final question. Would you recommend a student of electro-optica major to follow this kind of research or application or make some thesis work on this topic? Would you recommend? Of course,
yes. But actually, the reason is that because for OCT, the major impact of OCT is not on the photonic technology. The major impact is therefore, in the hospital, because in hospital you have the human value, right? In case you use this system, you can save one people's life. Even though the market size is small, still it's something very important because the human value is kind of you cannot count what's the value of a human life. Yeah. So in OCT right now, even though I mentioned this is the optical technology, so the penetration depth is shallow. The human body were very thick. So for OCT, these days, I didn't mention today, there are many different kinds of probe. So actually, the whole body can be imaged by using OCT. For example, in the vessel, right, in your heart, we can go through the vessel into the location. And people also have so-called needle probe. So with a needle probe, you can punch into your skin. So whatever the depth, you can have high resolution imaging. Yeah. So in the future, I think OCT can penetrate the whole personal body. And I think there are a lot of unmet need in the future for early diagnosis of the diseases, especially these days worldwide. The health expenditure for a country compared to the GDP of a country, how much percentage of the health expenditure? For most of the company, I think the country in the United States, in Europe, almost 20%. Okay, you can imagine so the health expenditure is very, very high. But in case for many of the disease, in case you can diagnose it in the early stage, then you can save a lot of health expenditure. So I think for OCT in the past is going very fast. I think imagine in case the people working on OCT really have more collaboration with physicians. Okay, I believe it's either we can have a large market size, you can save the human lives. Yeah, but the problem is that my personal experience is that it's very difficult to communicate with physicians or clinicians because for photonic people, when I talk to you, when you see the imaging, the first question you might want to see what's the depth, what's the size. But for physicians, they don't care. If you ask a physician, well, what's the diameter of a vessel, or what's the size of a cell? Most of them cannot tell. You don't care about the number. But the physician, they are very sensitive to imaging. When there's a small change, they can stop. So different specialty people, they have different expertise. Yeah. So it's very important to have a kind of cross-disciplinary education, collaboration. Thank you for the question.
Right.
Yeah, I have just a very quick question.
Sure.
So we know that through OCT we need a broadband source, but how low does we achieve? It doesn't matter, or does it matter how it can affect?
Yeah, you can estimate because I mentioned for cellular resolution OCT, there's a very simple equation. Okay, so you see the equation here. Yeah. So from this equation, it's very easy. You can estimate what the bandwidth, what the center wavelength, what the resolution. So usually, so these days, in case you want to have a cellular resolution, which means roughly is about 1 micrometer. So from the equation, you can estimate how broad you need. Yeah. So it depends on the center wavelength. Yeah, yeah, it's a factor of 2 difference. Yes, exactly.
In the case of the Gaussian language, because.
Yeah, only for Gaussian. Yeah.
Because Lorentzian is different.
Yes,
The
yes,
multiplying coefficient is a little bit.
yes, yes.
But
Exactly.
anyway, it's lambda squared divided
Yeah.
by. Yeah.
Right. Yeah. Yeah. So this is not exact. Roughly, you can use this
Yeah.
to estimate. Yes. Thank you.
Okay. The final question, in the product that you sell with the company of your spin-off, congratulations. How much is the cost of the hardware, that is the optical part, and how much of the software, that is the artificial intelligence? Are comparable, or optics is still much higher than software? I don't.
This is a very good question. But for the product we develop, when I do the technology transfer, we only transfer the hardware. But the AI is only something recent. So right now the company, they are developing the AI by themselves. So it's not related to
So
my
you
research.
don't know.
Yeah,
You
I don't
cannot
know.
evaluate.
Yeah.
Thank you.
And so, thank you.
Thank you. Devo firmare io le cose degli studenti.
No, poi abbiamo solo preso i nomi perché poi ci manderanno. Ok, so thanks a lot to everybody for attending and see you.
Can I ask a question?
Do you have a question?
Yeah, please.
Okay.
But like for you, not for the doctor.
Ah, okay, for me. Okay.
Okay.
Yes.
For the credits, do we have to send an email, or you are going just to see our names and send us?
You can send an email to me or to Martina for credit. Yes.
Well, actually, it's better if you type an email to unipv.usb
Yes,
at ieee.org, which is the name that is shown in my picture here.
Sorry. So this mail. So this mail address is attached to the mail.
Sorry, I didn't get your question.
Sorry.
This email address is attached to the mail sent to us about this seminar.
Yeah.
Yes, it's in the flyer, I think.
Yeah, also in the flyer, and you can find it also on the website. The website of the student branch of the IEEE student branch.
Okay.
And
right.
it is also the yeah, exactly. I can also write in the chat, and it's also the email who sent the no, that's not true.
Okay.
The one that sent the reminder.
Okay. Thank you so much.
Okay, bye everybody. Ciao.
Ciao a tutti.
Ciao, ciao.
Hi.
Bye.